Hello everybody, Happy New Year. It's been a year since we uploaded, but actually it's a month, like today is the 21st, but yeah, the last video was the 17th. Today, as you can see from our big screen, we're doing chemistry. And what are we doing? It's a topic we've done way back last year. And what we're actually going to do is we're going to redo this topic but in further detail. And we're also going to include some A levels about atoms, ions, and isotopes. Well, as I've said, we've done that before, and yeah, you can see this.
Probably impossible.
Yeah, we did this on YouTube way ago. But actually, we only covered the very basic facts of this, and it's actually only GCSE level. But GCSE sometimes lies to you, or sometimes it's very confusing. So today we're going to uncover the truth behind atoms, ions, and isotopes. Warning though, this contains A-level content, as I said. If you want to, in the GCSE test, you have to answer exactly how I tell you in GCSE format. Don't answer A-level stuff because then you get the answers wrong. Okay, so the key facts are both GCSE and A levels. So atoms are definitely made up of protons, neutrons, and electrons. That's easy. Protons have a positive charge, neutrons have no charge, and electrons have a negative charge. This is very easy. Like we've done this many times. And this is actually featured in KS3 and KS2 syllabuses, so these are easy. The protons and neutrons cluster together in the center of the atom, where it creates the nucleus, and the electrons orbit the electrons from far away. So remember last time, like our first lesson, where I've told you, like summer 2023, I've told you that this is what you think about the atomic model. Something like this. This is like this. That's helium, by the way. But it's actually, its real life scale is this. Like you can't even see the nucleus, and the electron is orbiting very far away. You can't even see the electron. It's just it's like a cross or something. You can't even see it. You can see neither nucleus or the electron. So really, atoms are mostly empty space, and it's really small. So far away. This is the sizes. So a proton is actually larger than compared to any other subatomic particle. Subatomic particle is something that's in an atom and smaller than an atom. Well, if it's in an atom, it's definitely smaller than an atom. And it has a radius of this, 1.7 times 10 to the negative 14th power meters. And that's 0 followed by 14 zeros, then it's 17. That's actually scientific. Let's go. Actually, protons vary a bit. It is not really it's not really the exact number, but there's an approximate. Neutrons have a little smaller than protons, like this big, with 0 followed by 14 zeros and 1.16, but they're actually the same, nearly the same, really. And this, to be fair, this is 1.65 times 10 to the negative 14th power, but forget that. You will not be asked that in the exams, sure. Electrons they don't have an exact size because we can't measure them. They're moving so fast. Like I said, they're moving quadrillions of times around the atom. We can't really spot them, and they are actually about 2000 over 1. 1 over 2000, the size of protons, which is like this big, is actually even smaller than the protons and the neutrons. So really, and I've added a point here that the nucleus is only about 10,000 over 1, the size of the whole atom. I said atoms are mostly made of empty space. There's a huge space between the nucleus and the electrons. So to be honest, the whole observable universe, if we just got out all the empty space and we put all the atoms, protons, and stuff in, what you actually can get is they're really small. Maybe like they're only like the size of your body, or maybe only the size of Earth. I've never really measured it, but it's really small. So let's go. This is helium-4. You can see this are the electrons. Often, because they're so small, we don't use dots. But actually we use crosses to represent them. And these are the protons, often represented as a circle and a zero in it, and the neutrons are often represented as a circle and a cross in it. They're actually very unique. There's no rule about how you should represent them. You can actually just draw crosses, and actually sometimes in the nucleus we just make it the nucleus or the element in it. Actually, it doesn't really matter how you express them. So this is a helium atom. And this is helium-4 and this is helium-5. What's the difference? And yes, electrons can be labeled as an E- or an X. Actually, the E- is actually like 10 times E-. It's actually used like this, and the X is actually on diagrams. You don't use X's on like scientific equations or something. So isotopes. So as I said, the difference between helium-5 and helium-4, because atoms can gain more than the number of electrons it is referred to in the periodic table. Like hydrogen on the periodic table, it has a number of 1.1007, I think, maybe this. And like the one is a proton, and it has 0.0078 neutrons, which is practically impossible. You can't have half or a part of a neutron. It's actually the probability of them being how many neutrons. So, for example, hydrogen can have 0, 1, or 2 neutrons. So, hydrogen with 0 neutrons would be like this. This is not a real diagram, even though it's not up to scale and it's not a real diagram. This is not how atoms really work. Hydrogen like this doesn't really exist, but we'll talk about that later. And it can have a neutron with it, and we can have 2 neutrons with it. I'm not going to draw that. The thing is, the stability of the atom decreases when it has more neutrons. Like it's like lifting weights. Hydrogen with no neutrons would be like a person standing by himself, where he can do that properly. If he doesn't have any disabilities, he can do that. And then if the atom has 1 neutron, he might be lifting a probably 20 kilogram something, and he actually can do that. It's probably stable. But if he is forced to take a 40 kilogram something, like 2 times 20 grams, 2 times 20 kilograms, he probably can't handle it. I can't handle it. And even if you increase the weight, it's harder for him to carry all these stuff. So, well, he becomes unstable and probably would collapse. That is about what isotopes are. Like, high helium can actually be helium-4, like 4 neutrons, helium-5, 5 neutrons. Yeah, it's probably more likely to be 4 neutrons for helium. Chlorine is actually something very different, 34.5. Minus the 17, so it has a probability of 17.5 neutrons, which means it's equally likely for it to have 17 and 18 neutrons. So there's a probability of 17 neutrons. It's actually equal to the probability of it having 18 neutrons. So chlorine is one of the only elements that have this, and both isotopes are very equally commonly found in nature. Yeah, and they both are very stable. So, well, these are the key facts about isotopes. Now let's see ions. Ions are kind of like the same as isotopes. They're not the same actually, because isotopes are about neutrons, yes, and ions are about electrons. Like, there are only 3 things in an atom: protons, neutrons, electrons. If you change the number of the protons, the atom's identity changes. Like, if you made 1 proton 2 protons, you make it from hydrogen to helium, which is not what you want. If you add or decrease the number of neutrons, you change the isotopes, and if you change the number of electrons, well, you change the ions. So atoms can also gain more and less electrons like neutrons than its protons. So as in KK3 or GCSE, you've learned atoms have 7 protons, 7 neutrons. That's practically that's a nitrogen atom, and it's balanced. It's a balanced atom, but atoms can be unbalanced, right? Of course they can. If you added a electron to a nitrogen atom, it'll be 8 and 7. It can exist. It can exist. It practically can exist, and that's how it exists. And it's the way how nitrogen exists. If it has 8 electrons, like it has a negative charge. We record it as nitrogen minus. If it has 9, it'll be nitrogen 2 minus. It's not minus 2, it's nitrogen 2 minus. So you could ask, an atom can have any number of electrons, can it? Well, yes, if you have the power of God to make it do that way. But anyway, if it has too less or too many electrons, this atom becomes unstable. For example, let's not say you're lifting weights. Let's say like maybe the weight of your top of your body and your bottom of the body. If they're balanced and well, it works. If the top is a little heavier than the bottom, well, it still works. But if the top is like 50 kilograms and the bottom is 1 kilogram, it isn't that normally balanced, and it can lead to problems. It's actually like this way. Yes, let's move on to the other facts. Wait, let me rub this out. Yes, good. Now let's talk about the electronic configuration. An electronic configuration is actually how atoms are arranged in shells. Shells are things that orbit the atom. Like this is an atom, and they have number 1 shell, number 2 shell, number 3 shell, number 4 shell, etc. So this is how it's arranged. And a shell can have infinite electrons, or it's not randomly placed around. It actually has a sequence. GCSE teaches you 2882, A-level teaches you 2882, 10. And in GCSEs, you only have to remember how they are organized, but in A-levels, you have to know how they are organized. So actually, it's s orbitals, p orbitals, d orbitals, and there's something called an A orbital. Yes, an A orbital, no other ones. You actually don't need to know the A, but you just have to know the S, P, and D. So the S orbitals just go in like a circle very easy. It can only contain 2 electrons at a time. A p orbital goes around like this, like an 8. It can also contain 2 electrons, and the d orbital goes around like this, and it can contain 4 electrons. So these are like the orbitals around the electrons. So 2, 8, 8, 2, 10, easy. So the first shell can only contain 2, second shell can only contain 8, etc. And for example, if we wanted to find the electronic configuration of chlorine, which has an atomic number of 17, you just have to do like this, Cl in the middle, 2 electrons, then out 8 electrons. Oopsie, this pen not good. And we see we have 10, and then we just get an 8. This shell should be 8, but we just draw 7. I'm not going to draw it. This video has limited time, so 7 are the most outer shell. Okay, so how an atom really exists is like our last point. Yes, it's our last point, yes. So GCSE kind of lies, and history and everything you've learned before about atoms, how it exists is kind of like most of it's a lie. They don't just exist in what you're supposed to exist. What GCSE tells you, 1, they just have neutral charge. 2, they have ions. 3, they are combined with others. But actually, the first can't exist, and part of the second can't exist. The thing is, the atoms must, except if they are radicals, which I'll tell later, they must have a full shell. Because they're happy with it that way. They must have a full shell. And if it doesn't, If it doesn't, it'll become a radical, which is number 3. Radicals actually rip electrons from other stable elements, which is bad because it makes them unstable. Like the nitrogen radical rips an electron from a stable H2O to get the full shell, therefore making it unstable. Well, you probably can understand that, can't you? Oopsie. Lost this thing. Yes, cleared it. So this is radicals. Radicals, they does not need to have full shell, but it's a radical. It can rip electrons from other stable things. Actually, radicals don't really exist. They exist for a very short period of time, like milliseconds. But if they were stable and they could exist, they could really cause much damage. The second thing is compounds, and like this is H2, this is H2O. H2 is like diatomic bonding. The two hydrogens share electrons. Like this one is here, this one is here. Because they bonded together, they actually both have a full shell of 2 electrons. This is H2O, and they also have a full shell. You can count yourself. Then the last thing is have an ionic form, which is being an ion, having extra electrons to make it a full shell. Or like the group 0 elements, they have a full shell in by themselves, like hydrogen, neon, etc. Which means they don't really react to others. In compounds, atoms actually will react to another atom with another element, for example, and they have a reaction. But if they have a full shell themselves, they probably wouldn't really react to anything else. Okay, so this is everything you need to know about our notes about atoms, ions, and isotopes. I hope you enjoyed the video, and I'll see you next time.